here are two great examples. So I'm stealing these examples. So although I guess I'm referencing them in, and you can see there on the screen. Okay, so this is this particular textbook. So I can't take any credit, but I certainly love these two examples because they capture kind of the electricity and magnetism as you're studying it through a foundational way. So it will kind of trigger some important items, bring out some formulas that it's certainly worth taking a look at. So here's the first example. It's an electron in a magnetic field. So if there's a particle with a charge, so basically just a single electron, and it's just being accelerated, and there's a final speed. So it goes in, let's imagine horizontally, okay, so that it's being accelerated. Now it's being accelerated through an electric field. So that brings back the concept of electric field, and here is a potential difference of 50 volts that we have. So we can bring out from the potential difference the actual potential, right? So the amount of energy that this electron would have, and it would be getting transferred to kinetic energy because it's picking up speed. Now, once the electron leaves the electric field, it will move through a magnetic field. Now, the magnetic field has a strength, so 0.35, and it is directed out of the page. So we want to be able to round all these things to two significant figures for our answers, and there's three kind of questions. So question number one, determine the speed of the particle at the moment it enters the magnetic field. All right, so what is exactly happening? Okay, so within here, so if we have some potential. Okay, so within here, maybe let me forget that and just say that we have an electric field which is going to be pointing, let's say, in this direction. We have this particle. Okay, so this particle is just a single electron. Okay, so it is going to be traveling in, and it is starting from rest, and then it picks up to a certain amount of speed. Okay, so as it leaves this electric field. Now, this particular speed, so maybe I'll just write delta capital V, so this is the potential difference, within here is governed by 50 volts. Okay, so you can see that in the question right there. So now, if we have that within here, we can actually certainly find out what is the speed of this particular particle as it moves along from one to another, okay, and then it enters the magnetic field. So how would we do that? So please recall, I guess I'll drop this delta within here, or maybe I'll just keep it just in case so that you don't confuse it with this little v here. So this is little v in terms of the velocity or speed. So recall that this is nothing else but the amount of potential energy that you have, so the electric potential energy that you would be carrying out, and it is divided by the amount of charge, right? So we know this is 50 volts. We also know that this has a charge of an electron. So that is, so right from the question, 1.6 times 10 to the negative 19 coulombs. So we can find out what potential did this electron have right here, right? So that is the amount of potential energy that it carries. Now, if that potential energy goes in and it exits, right? So this electron now exits over here. All that potential is going to get transferred. Now, where does it get transferred to? Now, we're assuming there's no other transfers to any other form of energy except to, as it's moving, to kinetic energy. So therefore, this is going to have a certain amount of kinetic energy. So the change of kinetic energy that you have is going to be equivalent to the change of the potential energy, so the electric potential energy that it carries. So with this information, we can certainly write this out. So don't forget, so this is 1/2 mv squared, that's your kinetic energy. This is going to be equivalent to the amount of potential energy, and in this case, this is nothing else but just your voltage multiplied by Q. So I am working with this formula and rearranging it from the definition of potential difference. So I have this, obviously I have the half. Now the mass of the electron, okay, sometimes if you forget, okay, so here it is, it's given within the question. So I also have that. So the only thing that I don't have is the v squared. Now I am going to rearrange this, okay, so as you write this out, so that means v is equal to, so I'm going to keep this in here, just drop that in. Notice this is going to be multiplied by 2. within here. So that's coming in, and then it's going to get divided by your mass. And then we have to take the square root, right? So within here, so if I take the square root, I will know exactly what the speed will be. And of course, we take the positive value out of that. So let's substitute all of these values in here, and you can do the same. You can pause the video. All right, so here's the answer, rounded to two significant figures, and you have it there on the calculator. I'm going to leave it on the calculator because I'll need it for the next component. So the next question that they ask us is determine the magnetic or the magnitude and direction of the magnetic force. So, please recall, so when you have this, so this is exactly what's happening here. Okay, so within here, so they said we have a magnetic field, and it was 0.35 Tesla. So let me just double check that. Yep, it's okay. So that's what we have there. And it is out of the page. So therefore, so it's coming out in this way. Your electron, okay, is moving along. Okay, so it's moving along in this way. So if you use your right-hand rule, okay, so within here, your right-hand rule is going to point in that it's going to be downwards. But of course, when we say that it's downwards, okay, so as you're going in here, that would be for a proton. So that means that the force is actually upwards because this is a negative charge. Okay, so the force is going to be up. Now the force itself is equal to, this is the charge multiplied by the speed it's moving at, times the strength of your magnetic field, and then the angle in between. So this angle in between here, so this electron as it's moving along, it is perpendicular. So therefore this is 90 degrees, and the sine of 90 degrees is just equal to 1. So now we can substitute. So what the charge is on the electron and the speed we have on our calculator, and then we have this. So let's substitute that in and find out what that magnitude would be. All right, so there you have it. And you see that on the calculator, just in case you're checking this in. So that would have been the magnetic force, right? So that we would have. Now the last question says determine the radius of the circular path. Okay, so if you let this go, you will know that, well, if you have a force which is present on this charge, then what's going to happen is it's going to push either up or down depending on the direction. In this case, it's up. This electron, and what the electron is going to do is going to start to shift over. So it's going to move like this, okay? And if you allow it, basically would create kind of a circular motion, okay? So within here, so this is where we're starting. So this is our electron. The force is upwards, right? So it's this way, okay? So within here, and it's going to be present as long as this electron is moving in that direction, and therefore it's just going to switch. Now, what does that mean? Well, this is the force, this is the magnetic force that is present, okay, that you have. And please recall, so I did a video on this one in terms of the radius. So what happens when you do allow a particle or any charge in a magnetic field? It's going to allow you to have that this force is going to be equivalent to the centripetal force, right? Because the centripetal force is the force around, okay, when you're doing a centripetal motion, so or circular motion all the way through. So don't recall, or please recall, okay, that this is just QV times B, and then this, of course, is just mass times V squared all over R. And you can rearrange this formula. So if you do this, you can cancel this off. You will notice that you're going to obtain mass times V is divided by QB. So we can substitute the mass, we can substitute the speed, we can substitute the charge and the magnetic strength, and then we'll get exactly what we wanted. So let me do that. There you have it. All right, so here again it is rounded, although I did use the rounded speed within there. I didn't go back and use all the decimal places. Okay, so you can just double check on that. but this is what you're going to obtain. So it's a really nice example, captures quite a lot of information within here from electric fields, you know, finding out the speeds, changing it over, using magnetic fields for the force. Great example, really like this one. Okay, so that's the first one. Here's example number 2. Okay, so it's to do with a mass spectrometer. You can certainly look it up and to see if you want to be able to learn what these actually do. So we have a researcher who uses this particular device in order to do some carbon dating experiments. So you can see this on the screen on the figure. So you have a charge. So this particular charge is coming in. Okay, it has a certain speed. It enters a magnetic field. Okay, so within here, so this one is right out of the page within here. And because of that, it will experience a force, which is going to trigger this charge to move with a certain radius, okay, at a certain curvature. And then there's an ion detector, so at the bottom there, so it catches, okay, these particles. So depending on what that particle is, what the charge is, etc. So we are going to be dealing with 2 ions. One is carbon-12, and then the other one is carbon-14. So notice that they're plus, so they're missing an electron within here. Now, they are going to be moving, or they're going to be shut out at a certain speed. So this speed is given to us as well. And then we know what this magnetic field strength is. So that is present in this particular spectrometer. And then we're given what the masses are. So here's the mass of the electron, and then here are the masses of the proton, and then also of the neutron. So it's a nice little bit of a deja vu with regards to that. So what we want to know is what the researcher, okay, based on first positioning, okay, this radius on this ion, okay, so as it positions this, okay, at a certain radius, so it's going to have a certain radius from here. So we can find that out, and we're going to be using in the equation that we actually used in the previous example as well. So recall that if you want to find what the radius is, this is nothing else but the mass multiplied by the speed it is moving at, divided by the charge, and then the magnetic field strength that we have. So we're going to be using this, and we're going to be using it for both of these, okay? So for this one, and then for this one. Now it says, how far must the detector move between detecting these two? Okay, so if it catches one of them, so let's say if this is the first one that it catches, so the radius for one of them is going to be smaller, the other one is going to be bigger. So depending on their mass, right? Because they're moving exactly at the same speed, they have the exact same charge, they're moving at this through the exact same magnetic field. So let's try to see what that difference will be. So that means we're going to be looking for delta D, okay, which is the kind of displacement or the distance in between as you move this from one point to another in order to catch these things through. All right, so let's get ourselves going. So the first thing, we're going to be calculating this, and this is going to be for the carbon that we have. So this is for carbon-12. So that's the first one. So what is going to be that radius? Well, we need the mass, okay, so for this. Now, by the way, so, you know, how are you going to find the mass? So you're going to have to recall a little bit of your chemistry, how these things are set up. So I actually did this beforehand. So here's the mass of the carbon-12. So what is it composed of? It's composed of 6, okay, of the protons. So we need 6 times the mass of the proton. That is given in the question. We need 6, so we're going to be adding it to 6 of the neutrons. Okay, so that's there. So that's what makes it 12. And then we have 5 electrons, which are in there. Now the electrons are much smaller than the actual protons and neutrons, so they won't make an enormous difference, but here it is. And then here's the result. So this is rounded to 4 digits for the moment, 4 significant digits. And then for the mass of the 14, so here it is, the same exact process. So this, you know, just reminds you on how to capture that mass. So we have these 2 masses. Great. Now we can take these masses and we can substitute it in. So I'm going to first substitute it in for the first one, so for the carbon-12. Let's see what we get. So here's the first result that you see there. So I'm not going to do any rounding. And now we're going to need the second result, which is for this one. So we're going to have to plug in the mass, speed, charge, okay, etc. So let me do that, okay, for the second one. So there you have it. So notice that for carbon 14, the radius is bigger, and that should make sense. You know, the bigger the mass that you have, you know, the harder, because, you know, there's a force which is present on it. So there's more inertia, right? So more inertia in terms of the mass itself. So it's going to be much harder to try to, you know, swing this particular particle all the way around. So the more and more mass that you have, you know, the bigger and bigger the radius is going to get. And then hence, you know, the spectrometer, which allows us to capture these things in so that we can figure out what these ions are. Now that we have the radiuses, we can finalize and kind of decide on how far that detector has to move. So don't forget that this is a radius. And so that means, you know, it goes from right here to right here. So as you're moving along, so for this one, the distance, okay, so from here to here is obviously double. And so that's something that we have to think about. So this is doubled. And if we want this would also double, right? Because it's the diameter. And therefore, so if you're calculating what that difference will be, then it is equal to twice, okay, because of the diameter, and that would have been the radius of the 14 minus the radius of the 12. Okay, so let's substitute that in and find out what that answer is. All right, so there you have it. Okay, so this is just rounded to 2 sig figs. You can obviously round to any that you like. All right, so that is it. Okay, so for this example and for both of them, I hope that you found them useful. Thanks for watching. See you in a future video.